Welcome back, episode 28, Get a Grip on Lighting. On today's show, we have Dr. Paul Rudy, the co-founder of SLD Laser. What is SLD Laser? Huh? We thought we finished off this whole lighting game, did you? You thought there's nothing going to take out LED? Well, son, you might want to listen to this show because Dr. Rudy told us a lot about the possible applications for laser. This episode of the podcast, Greg, who's on this intro with me, is brought to you by who?
SLD Laser, none other.
SLD Laser. Go to SLDLaser.com, SLDlaser.com. Greg, I think he convinced me on this one that there's space in this business for these laser applications. I think there is.
Oh, for sure. A lot of our podcasts, we talk about the importance and the quality of getting the right light where you need it. And this sounds like it's the best source that's out there per our discussion today is in terms of center beam candle power delivered, foot candles delivered lumens. Laser is probably the best source that can actually get you what you need, where you need it.
I think they position themselves well as that kind of like a Qualcomm where they're just going to supply the components and then they're not trying to take over the whole business. They're going to supply components to the traditional manufacturers who are going to sell it to the distributors, and then they can use those components and the innovation will just go nuts from there because I think there's the applications are endless on the outsides of this industry that LED just can't serve.
Exactly. A lot of manufacturers have done different technologies, different light sources. Now they can do LED lighting. They can have laser options. They can really meet every need that's out there. And I think laser really fills that gap. I don't think
there's any need to displace LED. I think there's tons of room for laser lighting outside of LED applications. Joey, throw the SLDlaser.com website up there for the YouTube viewers. So if you go to SLDlaser.com, that's SLDLASER.com, man. Go to SLDlaser.com, especially if you're a manufacturer and you're thinking you want to get ahead of the game, Hassan. You got to go to SLDlaser.com. And this episode and every episode that's on the GetAGripOnLighting.com website is sponsored by the National Association of Innovative Lighting Distributors. Go to NAILD.org, Greg. Go there. Take LS1,
Absolutely.
Man. Take LS1.
That's where we got our start.
That's where we got our start. Take LS1, LS2. And episode 28 with Dr. Paul Rudy of SLD Laser, Get a Grip on Lighting. Welcome to the Get a Grip on Lighting podcast, Paul.
Thank you. Appreciate the invitation to speak to you guys today. It's great to meet you both.
Say hi to Greg Eric.
Greg, hi. Paul here.
Hi,
I'm
Paul.
in Los Angeles. It's great to talk to you.
Yeah, definitely. Out of Minneapolis, Toronto, you got the whole country covered.
Yeah, it's a virtual studio.
Continent. There you go.
So tell us a little bit about why you think LED is not the end game here, Paul, because everybody else we've had on this show says it's over. LED is the end game for lighting. Tell us why you don't believe that.
You bet. Yeah, the vision that we've developed over the years is that LEDs are wonderful for flood illumination. They're incredibly efficient. Their color quality's great when dialed in properly, and they're quite reliable. However, if you want more light out, you need to add more LED area. Therefore, optics get bigger if you want to control the light, and you end up having challenges in any kind of small optic, long range, collimated, or precise sort of lighting control setting where you're trying to create precise patterns. So we think where lighting is going will require additional fidelity control over the light patterns, even invoking light to do more than just illuminate, maybe help sense or help communicate. And given all that, we think laser light's an ideal solution.
Are you familiar with halogen MR16 technology?
Yes.
So you're talking about like an ENX, EXN, BAB, so different, very, very, very accurate beam spreads coming out of very small light sources like MR11s and MR16s. Is that kind of what you're referring to?
Yeah, I mean, to give you a concrete example, we're getting, say, 500 lumens from a few hundred micron spot. This means if you go to a 2-inch optic, you're talking about a degree or less. 1-inch optic When we put that into like a flashlight configuration with, say, a 30 millimeter diameter optic, you end up with kilometer range. So the portable lighting folks are using the 1.5 degree beam angles for all kinds of exciting effects. Initially, this isn't replacing LEDs. This is augmenting LEDs with something highly directional. And actually, the same story is happening in automotive. The high beam effect is now adopting laser light, but the low beam, the daytime running light, these effects are still being generated with LEDs and are expected to for the foreseeable future. So this idea of kind of a hybrid solution where you need laser light for the precision, directionality, low beam angle, MR16 as an example, that could be a nice application for laser light. But if you're looking for, floods, LEDs are just fine.
And I think you said the word initially, it's not that. Do you ever think that in the future it will be LED versus laser?
Yeah, I think there are lots of future applications that will move the direction of wanting laser light increasingly, in sort of a long-term horizon. It's funny, so one of my co-founders, Shuji Nakamura, won the Nobel Prize for the invention of the LED. And after he did, they said, what do you do next? It's like the question, you win the Super Bowl, what do you do next? And they say, oh, we're going to Disneyland. Well, instead of saying he's going to Disneyland, he said, we're going to laser light. This idea of lasers increasing in efficiency every year pretty dramatically, and lots of chips per wafer, where the lasers generate maybe 10 times as many chips per wafer. Both these things over 5-year plus horizon indicate things like lumens per watt or dollars per lumen eventually laser light can catch. So initially, for sure, it's directionality, it's precision, even waveguide delivery for some really wonderful effects where you can pipe the light through fiber. Those kinds of applications are going to be laser light right away. Longer term, more general illumination, cost has to come down, efficiency has to go up for laser light to take hold. And we think there's a future there.
What are the current lumens per watt of laser? What is the capability?
Yeah, so just source-wise, it's in the 50 to 75 lumen per watt range. So this is at temperature, just the source, roughly, half that of LED. Lots of, LED lumen per watt figures out there might be pulsed or cold, meaning not at temperature, sort of on continuously. But even with sort of an apples to apples, we're somewhere between a third less to a half of the lumen per watt. So the areas that we see adoption now are where the delivered lumen per watt is what matters, right? If, for example, in a high beam, in a portable hand light where they're trying to get range, when you're trying to get into a waveguide, these kinds of things.
So I don't like lumens per watt as a metric for. Yeah. I think it's a rough metric of what you're getting. I think delivered foot candles, delivered lux, whatever it is. So you're saying that even at 50 to 75 lumens per watt, you can deliver the lux much further and more accurately than LED right now?
That's exactly right. So if we actually have a really neat calculator we developed to look at different applications. And if you freeze the optic size, right, because you can get collimated beams if you make, an LED source with a dinner plate size optics, right? But if you freeze the optic size of something like an inch or two diameter, right, and then you look at the lumens coming out and you start looking at the delivered lumens per watt, or the lux, as you say, after, depending on the source and the configuration, After a few meters, certainly above 5 meters, your delivered lumens per watt, laser starts running away with the race. And that's because of the low beam angle, and your just intensity is falling as R squared. And so in different applications, we can do that assessment. Again, if you're just lighting up an office in sort of Lambertian emission, that's no problem for an LED. But once you really want to put, let's say in an architectural lighting configuration, you want to frame a picture, or you want to, in a distributed lighting application, you want to put light into a waveguide and either have it be transported or have the waveguide itself be glowing, so it's like a light wire. Those kinds of things, really, lasers win the day right away.
Is there a minimum beam angle and a maximum beam angle of laser lighting?
Great question. So the exciting thing about what we're doing is it's a point source, right? We're really generating light from a few hundred micron spot, and therefore all the lighting designers, all the luminaire designs can leverage this to control the beam. That point source means that, if you use a 1-inch optic, you get a 1.5 degree beam. Wonderful. You can absolutely increase that if you want a 5-degree beam, if you wanted a 40-degree beam, with things like diffusers, or even just controlling that with the shape of either the optic or the shape of the reflector. So going to higher beam angles is always possible. In fact, one of the really nice demos, I can show it to you today over my shoulder here. You can go from a spot to a flood with kind of an electric lens kind of a thing. And we start with a couple degree beam, and then you can go to 30, 40 degree beam with a Bluetooth app, right? And it's a little liquid crystal plate put on the front that one of our vendor partners makes for us. So that increasing beam angles, no problem. So in applications where we call it sort of spatially dynamic, right? Where you want to control the light pattern.
I'm thinking theatrical lighting. Theatrical lighting is
theatrical lighting, absolutely. Folks in automotive coming down the line are literally shaping the light to avoid glare of oncoming vehicles the other way. Autonomous vehicles are going to be doing this actively, where you can shape, dim and bright patches accordingly, all autonomously with camera systems. That it's the long-term vision for that is essentially having a projector in a headlight, right? And one could imagine the same kind of thing in next-gen smart lighting, where you have the ability to shape the light. The TI DLP is an example there. If you look at projection display, that went to laser light back around 2010, 2011. The étendue required to keep the costs small, the optics small, the DLP chipset small, drove everybody away from LED and to laser pumped phosphor solutions because of that. So that's broadly adopted now in projection display, say over 500 lumens. And same kind of thing in spatially dynamic lighting. If you start with a kind of a point source, then you can control that light. In addition, even if you want static control, even if you just want to put out a pattern, we have, low-cost diffusers we put on our spotlights. We can generate, a 60-degree by 1 degree line, as an example, or really have sharp contrast of beams. That all goes back to the point source nature of the light.
Will it ever have the capability to be omnidirectional?
Yeah, I mean, what we're doing with a laser pump phosphor configuration, we start with a laser, right? So this is just a blue laser pointer. I'll shine it over here. We then hit a phosphor, and so this is a surface mount package as an example. Oops, sorry. That's a surface mount package. It looks a lot like an LED surface mount package, actually. This happens to be 7 millimeter. We have high power lasers in there, and they hit that phosphor, and the light comes out Lambertian. So it's at least in 2 pi sterradians, hitting sort of 180 degree Lambertian. But the trick is it's coming from a tiny point source, a few hundred microns. So then when you put a TIR optic on it, when you put a reflector on it, the same you might use with an LED, you get essentially 1/10 the beam angle that you would with the same kind of LED source in a similar style package. So one could design a laser pump phosphor that literally illuminated in 4 pi sterradians. One of the reasons we don't do that today, it would be like a laser pumping, just a point source phosphor that's illuminating all over. One of the reasons we don't do that today is for safety. So safety-wise, everything we're doing is reflective mode phosphor. So we're shining high power laser light onto a phosphor in a reflection mode, kind of at a glancing angle, and the Lambertian emission then comes off of it. So if the phosphor were to crack, the phosphor were to fall off, whatever, something catastrophic happens, the laser light's inside the package. When you do a transmissive mode configuration, which we're not following at all, if the phosphor goes away, you're now putting out high power blue laser light into the world, and that's something we wouldn't do.
Why
so
wouldn't you do that? Is there a danger? Is there a danger with that?
Yeah, absolutely. So if you end up using a transmissive phosphor configuration where failure modes would enable laser light going through the world.
Transmissive, you mean laser going through something and out.
Exactly.
And then that thing falls off. And the laser's just going out.
Then you have laser light in the world. So all of our designs, all of our implementations, every product we're making uses this really wonderful reflection mode. And so we put chips co-packaged with the phosphor.
Let me ask you, what would go wrong? What would go wrong if high heat blue laser came out of the light fixture? Is it dangerous?
So just regulatory wise, the projection display world went through this years ago. Regulatory wise, for direct laser emission, you're allowed up to 30 lumens for a direct laser. Laser pumped phosphor, which we call laser light sources, 5,000 lumens plus, CE mark, UL certified, no problem. So the point there is incoherent light goes into the world on a projection display screen, or in our case from a light source, and it's inherently safe and regulatory wise approved. So this is really an important aspect of the commercialization of laser light that we're bringing for lighting, which is a safe implementation. We're using a reflective configuration, and incoherent light goes into the world. It ends up being classified as LED light. It's Lambertian incoherent white that we're generating.
So you've kind of touched on the chip, but what are the components? Is there a driver or something that fires the actual laser? How does it all work?
It's really similar to, let's take first a typical LED, and then I'll describe what we're doing in laser light. Typical LED would have, let's just say, a blue LED, would have phosphor on it, right? And then it's generating white light from that. And so you have certain drivers and heat sinks and optics that you put on that. What we're doing is quite analogous. We have a blue laser hitting a phosphor, white light comes out, and it's incoherent. It's just from a tiny point source. The same kinds of drivers can be used as LED drivers. The same kinds of optics and heat sinks can be used. You're simply getting this incredible benefit of this high luminance candela per square millimeter, as an example metric, that's 50 to 100 times brighter than an LED. So therefore, if you say similar driver, similar optics, similar heat sink, you end up with 1/10 the beam angle from the same kind of configuration.
What's the difference between this and plasma, light emitting plasma? It sounds very similar to me.
Yeah, plasma usually has some RF, some radio frequency that induces in a gas some plasma, and light emission comes out. There, the light emissions usually in kind of a line, but it is high spatial brightness. You get a lot of light from a small source, say a few millimeters big. Typically, you can get 10,000 lumens plus. What we're doing in laser light is we put electricity into this chip. It's just like a Blu-ray chip, or that sort of thing. It's just higher power. Electricity goes in. Blue laser light comes out and allows us to hit a tiny spot on the phosphor, and then white emission occurs. So it's really more analogous to LED technology, meaning it's solid state, versus plasma, which is sort of RF induced in a little gas. So really, that's a different technology.
Are you a sales rep for this company? What's your job?
So I'm the co-founder
Do you sell this
and
stuff? Do you guys
chief
do you go out
marketing
and sell?
officer.
Do you go
What's
out and
that?
sell? Do you go out and sell?
I do, absolutely. Yeah, yeah.
Okay.
So I'm SVP of business development. You bet.
So because you're very techy. Like when we talk to you, you have all the tech down. I'm not sure everyone's following that is listening to this would be following all the technological words you're using. So, and I'm not totally clear. What is the fundamental difference between this and LED? It's a laser, but what's the difference between it in layman's terms?
The light coming from a tiny spot, and that means you can get beam angles that are 1/10 the size as an LED.
But it's still classified as an LED.
Correct.
Okay.
It's classified as an LED from the safety and regulatory perspective. In fact,
one way to put it. Oh, go ahead.
Pardon me?
I was gonna. You finish off, and I got a question.
Yeah. The configuration of product we're making in an SMD, it looks and feels like an LED component that's being integrated, but the spot size inside of a mission is 1/10 the diameter, and that gives incredible benefits from the luminaire design. And we've had a bunch of folks design this in, so maybe some examples would help.
Sure. Yeah.
Yeah. Well, one thing maybe on the layman's side, because I'm usually better at that than Michael is here. But would the argument be center beam candle power? Would that be one that you could really relate?
Center beam candle power. That's right.
Okay.
So in a case like this, here we're delivering blue light through a fiber to a phosphor head. So this is a kind of a distributed lighting source. In this case, you can take the laser module, put the driver, the heat sink, everything away, right? And this is just a short fiber, but we've done a 10-meter pole light at the Shakespeare Globe Theater as an example. The light comes out of this little phosphor head, and with a small luminaire, you can generate really wonderful sort of remote lighting effects. So you could imagine long-term pole lighting, this being excellent. You can have everything at the base of the pole: electronics, heat sinks, drivers, the laser chips themselves, just a passive, in this case, armored cable carrying the light up in a little phosphor head with a reflector at the top. So that's something that one couldn't do with an LED, and it's possible because of the point source nature of laser light.
And the laser's going up through that cable. The laser's going up through that cable and hitting that phosphor chip at a certain angle, and then the light is delivered.
That's right. And here's an example of it. And so the point source nature of this light is incredible. If you were here, you could see literally the hairs on my arm.
Oh, really?
And I'm not that hairy of a guy, but you can literally see the hairs on my arm because of the fact that it's coming from such a small point source. Well, who cares about that? Well, if you want directional light to shape it, let's say you want to generate narrow strips of light from a pole light just to put the light on the road and nowhere else. Let's say you want to generate lines on the road, literally. Let's say you wanted to shape the light and have 100-degree by 2-degree beam because your pole's generating a path light. That's possible, and not possible with LED. In the case of, say, the SMD, this is the other product. This looks like an LED SMD, but when you put it into just a tiny little, this is an LED style TIR optic, and 35 millimeters. So when you put that into a beam, maybe you could turn on. One of my colleagues here is just going to show a beam at a couple meters away. That's with a diffuser on it. Without the diffuser, yeah, it's a really tight spot. And so putting a low-cost diffuser on it, you can create, in this case, I think that's a 60-degree by 1-degree beam. So the lighting effects, architectural, outdoor, entertainment style lighting folks are looking at this precision light control. Sometimes it's a fiber delivery remote. Other times it's just simply a tiny microspot module to give these collimated beams.
What's the maximum distance it can spread light or shoot light?
You say a kilometer?
Yeah, so the ANSI spec, like the spec for a flashlight, is the distance at which you deliver 0.25 lux. Okay, so that's the spec for what the flashlight range is. Typical LED flashlights with a couple inch diameter, they're going to be 200 meters, and those are usually larger optics. If we go with a 30 or 35 millimeter optic, we're at a kilometer range. And we could show you some,
not many Americans,
a video running.
Not many Americans have a kilometer in their head. You better put it into miles for Gregor there. Is that 0.6 of a mile?
It's 6. Yeah, that's right. 6.2 kilometers. So in
0.6 miles.
10K is 6.2 miles. Yeah.
So 0.6 of a mile.
0.6. So if we look at that effect, we've got here's some off-road lights. You could imagine the community of Jeep racers and motorbikes. This has 4 of them, right? Neat little reflector set. They're using the same. This is an off-road lighting company called Baja. They're using the same kind of optics as an LED optic. Same kind of drivers, same kind of heat sink. In this case, there's 4 of these, right? And so you get up, toward half a mile pretty quick. Search and rescue, the folks are doing some of the entertainment spotlights.
You're about to go. Is there any? What are the military applications for this? And have you been in contact with anyone from DARPA or the U.S. military or the Pentagon about this technology, or did they give it to you?
Yeah. So you can imagine just something like this is really exciting for say the special forces folks. You can imagine the handheld flashlights would be really exciting for folks that want some asymmetric illumination. But even honestly, in police, fire, rescue, search and rescue, disaster preparedness, you want to be able to shape the light. You want to be able to maybe just do a horizon view of 5 degrees by 60 degrees and scan that. You could do that with a really compact kind of handheld light source. So yeah, there's a lot of security, defense, outdoor portable applications, but even vehicle mounted, right? You could imagine there's a marine light crowd. So these are the early places that laser light will see the market here later this year and next year. You'll hear about this.
You talked about connectivity as well.
Yeah.
Can you send a high-speed Wi-Fi internet signal down that laser light?
Yeah, so it's a really good question. The answer is yes. We've demonstrated 8 gigabit per second with just one of these 500 lumen white light sources. What's happening there is we're using blue laser to pump a phosphor. That's wonderful. The laser itself is really fast. Really fast. That's why telecom uses lasers. That's why fiber optics uses lasers and not LEDs. So in principle, we're looking at 10 to 100 gigabit per second being possible from laser light. And with LED, it's challenged because of just the nature of the chip. So we're thrilled about the future of laser light. We've done some early demonstrations where some end users basically hooked up special electronics to our standard source, and they're playing an HD 8K resolution movie across the in 3D across the room just by streaming. So this smart lighting move toward Li-Fi is something that laser light's a really nice fit for. There are also ways you can just pulse the light and get depth, right? So you can end up with a sensor. If you add a low-cost sensor, you can end up wherever the light is shining with some time of flight measurement. And because lasers can be pulsed really fast, you can end up with basically a LiDAR or depth coordinate.
That's what I was thinking
where
about.
the laser light's shining.
Yeah, and I mean, you think about a kilometer. So most satellites are a kilometer from Earth. Like if satellites going around the Earth, they're about a kilometer or 2 kilometers up there. They're not that high up there. Isn't there an application for this with that communicating? I don't know if the radio signals or how it works. I mean, couldn't you communicate with enemy satellites with this thing? I don't know. I'm always thinking conspiracy theories here. So, I mean,
in general, I think the question we would always ask is, you could do that with an infrared laser that isn't visible to the eye,
okay. Sure.
and those are used in telecom, and so that's wonderful. What we're doing is white light illumination. So if let's say in an application where you have the light, right? You've got the white light, and would you want to communicate? So, for example, smart city, smart car applications. Laser light's in the vehicle anyway for high beam, and that's great. Well, it can transmit to street lights or other sensors in the city and transmit data. These autonomous vehicles are going to be unbelievably heavy with data. All these sensor suites, right? And in some cases, you're going to want to exchange data. So if laser light's moving into some spotlight applications in some, say, stadiums, in outdoor venues, now you can flood even areas and just leverage the fact that lasers are so fast and transmit data in areas where usually it's tough, say in a crowd, where you're trying to watch video, watch highlights of the game, whatever, and you just can't get a Wi-Fi signal. You can't do it. So laser light's ideal for that in the longer term.
Is there anyone else in lighting that is using laser technology or developing it, or is it a patented idea that only SLD has the use of?
Yeah, we're the only ones bringing it into lighting. There's a couple of folks that are making more sort of auto headlight assemblies that are configured for larger headlamp, but for lighting, this kind of configuration or this distributed fiber kind of configuration, it's really unique. And just at Light Fair and Light and Building, we had half a dozen different groups showing different products. There's an architectural lighting, like a track spotlight, right, where they always wanted a 1 to 3 degree spot, and they couldn't do it with LED from a tiny luminaire, and so it's starting there, and we're the only ones that are bringing it to market. It's really tough. So that the 3 really critical pieces are: you need the blue laser chip. We make that in California. You need a special phosphor chip that can withstand high intensity, right? Otherwise, you'll just cook the phosphor. You'll have a little barbecue inside the package. And then the third is the integration of that. You got the package, you got the phosphor, and you've got the laser putting it all together. And so, as a result, those 3 technologies are pretty unique to come by, and Professor Nakamura really pioneered this.
What do you think, or when do you think the average lighting distributor will really be able to promote laser products?
Yeah, so it's just the very first specialty products are coming out in the second half of this year from our customers.
Yeah, I was thinking
Right. And then in 2019, it will, I think those products will really start to see the light of day. So I think 2019 is where it starts, where luminaire manufacturers will have our SMD or fibers inside, and they'll start to see distribution line cards and different applications all over. There are, I'd say in a 2 to 4 year time frame, we see this eventually in retail. Some of the indoor applications really start to open up. As you may have sensed, we're starting in outdoor. We're doing that because the range, obviously, and also the outdoor color quality and CRI is a good match to where we are, which is around 6,000 Kelvin and 70 CRI. I was going to say,
do you have any other color temperatures? That was going to be my question.
Yeah, so we just showed a 4,000 Kelvin and are just starting down toward 3,000 Kelvin and getting the CRIs up 80 and toward 90. That is active work in progress. So if you ask sort of what are we working on, because it seems like the directional stuff is where we're starting. We're working on the warmer colors, the higher CRIs, and that's again in this sort of 2 to 4 year horizon where we'll see that. And so I think the outdoor folks will see it, 1 to 2 years starting. The indoor folks will see it in more like 2 to 4.
Before you came on, I actually didn't think the bird would fly, but I think you got a good business case here. I think I'm starting to see a lot of applications. Have you guys thought about the health effects of lighting at all? Because other people that have been on this show that have talked about lighting's health effects are always talking about quality of light and then quantity of light. And then, being able to really get people into high light areas so that the Alzheimer's patients were this table where they put this stuff on and then a lot of lumens comes out of it at certain times of the day. Have you guys had any people from that area of the lighting business talk to you about lasers?
Yeah, so it's a good question. We've had this incredible precise control of the light. Means you can put it exactly where you want it. I'll show you an example. This is a fun one of fiber light, right? So this is plastic optical fiber. And we can precisely put in light, and there's a little bit coming out. In this case, we're using a side scattering fiber intentionally, so it would give this effect. But also would leak a little bit out the end. So you could do this either 100% transport, or you could do it 100% scattering, and this is a little of each.
How many watts is that? How many watts per foot is that?
Pardon me?
How many watts
per
foot?
We're putting in around 300 lumens, and this is probably 10 feet. So that lighting effect, and we've done this in 10 meters. We've done this in like 30 feet. It's absolutely beautiful. And so this stuff, when you can imagine all the entertainment and architectural folks, even potentially daytime running lights eventually in auto, it's like 1.5 millimeters. This means you can put light into waveguides. You can even put it into films. You could put it into blankets. You could put it into fiber meshes to really distribute the light. And depending on the color you want, right, you could then have a really nice area. It's very difficult to do that with an LED, right? If you take an LED and try to stick it into a waveguide, you don't get much into it. In this case, for example, it's like 1 millimeter fiber. You might get 5 to 10% of the light in. In our case, we're getting 60, 70% of the light through the fiber. And so that kind of effect can be used in any kind of area we're trying to put light into the body or onto the body carefully. And that's, again, this precision light control we think's important. And as when you stop and think about it, the application of light where you're just floodlighting a small area is a subset of the vast universe of lighting applications where frequently you really want to put light where you want it. And that delivered lumen per watt or delivered lux is the key.
And is there any concerns over operating temperature of a laser light?
Yeah,
In terms of the environment?
it's a little bit younger than LED. So think of where LED was, 3-4 years ago, meaning we're not as efficient today, and we're running chip temperatures on the inside up to 100, 110. LEDs run 130. So right today we're running a package like this. It could go up to sort of the environment, go up to 60 C or something. So they're pretty robust. I mean, these guys are going into vehicles, they're going into portable lighting, but just head to head against an LED, it's a few tens of degrees, preferred lower. It won't turn off. It just will dim more than an LED does at temperature. And that's about technology maturity. It'll take, we're sort of following the LED curve, but a couple years behind it.
Does it perform similarly in the cold to LED, where it actually operates better?
Exactly right. Yep. It's the same kind of chip, and it does. Yep. Yeah.
And on-off does not affect it at all. The cycling on-off.
On-off, it does not affect it at all. Yeah, you can pulse, really any pulse you want, and
I don't know if I believe that. I don't know. Everybody says that, but I don't know.
Yeah. So let me describe the chip itself. That chip is mounted with hard solder, like the kinds of used in telecommunications or mil-spec kinds of applications. So the on-off cycling is proven at sort of the device level. What we've seen is, when you get the electronics or heat sinking involved, that's critical. It's critical in LED systems. It's critical in laser light systems. But the fundamental sort of technology of putting a semiconductor chip laser with a phosphor robust with on-off cycling.
Wow.
What is the hour rating of the laser light?
Great question.
The chips we're making today are around 15,000 hours and headed toward 20 to 30,000. Again, it's sort of, think about where LED was a couple of years ago, and it's been increasing every year. If you look at the curves of all the key metrics of sort of how efficient are these, how much power do you get out, what's the reliability, it's increasing year by year, and that's one more example.
And it's rated the same in terms of at the point at which 30% of the light is lost is 15,000 hours?
That's right. Yes, it is.
Okay.
Mean time to failure, 30% degradation defines loss, you bet.
Is there any capability of ever having your laser lighting products, or are you going to follow suit with LED where you try to make it future-proof, or that term, and make replaceable parts with laser in it? Is that the goal?
One really exciting thing about what we're doing, these chips are tiny. They're really small. They're like a tenth the size of an LED chip. So putting some redundancy in, is possible, which is a way to extend life, of course. And some of the automotive applications, that's something we're looking at.
So you want to sell the components. You're not making fixtures. You want to have manufacturers adopt this technology into their product lines.
Yeah, what we're doing to help aid that process is we are doing reference designs. We are doing demonstrations where we recommend the optic, we recommend a driver heat sink, and we're working with complementary technology providers in that way. But we're really excited about getting this into the hands of as many luminaire makers and integrators as is possible, because they could do a whole lot more with it than a 100-person company can. We have a chip fab. We're working to get better CRI, warmer colors, and just drive the technology forward in efficiency and reliability and all that great stuff. And we think we'd love the ecosystem of lighting to adopt it. Let us do our thing. Every year we're going to be coming out with a better source, and the expert folks that make incredible hardware like this. And already have distribution channels. That's we want to partner with the best and leave it to them.
Very Very good.
Well, you know, David Nathaniel came on the show a couple podcasts ago. He owns a big lighting manufacturing company in Canada, and he was regretting the loss of precision in lighting. He was saying that you can't really do much with these LED panels. It's like everything's a flood. Everything's a flood, you know. And I think interesting. Greg and I were talking about you before we came on, and we weren't sure where this was going to go, but I see a future for SLD Laser. And I don't think it's going to displace LED. I just think it's going to be more options for everybody. And I think that's usually when something does get adopted. It's not when it's a complete. Not often do you see a total disruptor like LED. Like LED came along and completely disrupted the lighting business. You don't see that a lot in industries. Usually you see complementary technologies filling a void, say. And I think there's a void here, and I think you've pointed it out. What's the website of your company?
It's SLDlaser.com.
I think that's a podcast.
We appreciate your input. I think this bringing sort of legacy point source light brightness to solid state lighting is really exciting. And you know, that's our vision, and that's what we're going to be working to fulfill. And as you say, we're going to be working on the best engine possible, so that our luminaire and distribution partners can carry it out to the market. So we're thrilled about it, and appreciate you having me on.
Are you convinced, Greg? I can think of some customers right now.
I'm
convinced.
I'm
convinced by it. Yeah, we got to see some pictures though. All right, man. Thanks for coming on the show.
Thanks
very much, guys. All the best.
Whew. SLDlaser.com. That's SLDLASER.com, baby. SLDlaser.com. Greggy, that was a convincing case, man. I don't know when it's going to come to market, but when it does, I think you're going to see a lot of laser lights out there.
Yeah, I'm excited about it. I think it's something that, you know, we need in this industry is always constant innovation. LED is there. It keeps getting improved upon. Controls are there. They get improved upon. Let's throw another technology into it. Let's keep this thing confusing.
Yeah.
Get some LED lighting going, or laser lighting going.
You know what? I think Dr. Rudy took what was confusing and made it pretty obvious why SLD Laser has a business case in this game. And I think a lot of people have been ignoring it because the message has been, hey, LEDs are efficient. We're there. We made it. But we're leaving behind a whole bunch of applications that I think laser can fill.
Yeah, it does seem like it really fills that gap and that need. And I'm excited that it's here and ready for it to be on the market for us to sell it.
Yeah, I mean, I don't know. Do you think it's going to go into like an LED lamp or something? I mean, he's saying we have the technology, take it and run with it. Is it going to be purpose-built LED luminaires? Is it going to be purpose-built laser luminaires? Is it going to be screw-in laser lamps that are connected to the internet? Who knows, man? But I think the future is wide open for this technology.
For sure.
There's a huge space. Yeah. Dr. Rudy, thank you for explaining it. Listeners, manufacturers of light fixtures and lamps, go to SLDlaser.com. That's SLDLASER.com, baby. SLDlaser.com. And Greg, we got to talk about the National Association of Innovative Lighting Distributors, who sponsors all the shows on the GetAGripOnLighting.com website. Can't even say it. GetAGripOnLighting.com website. Why nailed, Greg? Why now? Why nailed?
I think it's one of the best associations out there for lighting, if not the best. It really brings thought leaders together, people that are hardcore lighting people, lighting geeks, lighting dorks, getting after it, and really trying to figure out what the next step is and how to stay relevant in the game. That's where Nailed steps in and really elevates or gets us all up to a level where we need to be in to succeed in the future.
Yeah, without this podcast, I mean, Nailed would be the only place for really light bulb sellers to get a focused, people that sell lighting systems to the end user, to get a focused update. The conference would be the place where you get an update on everything that's going on. So if you come to that Nailed convention, you're going to meet people like Dr. Rudy and Christian Monrad from the Dark Sky Association. All this kind of stuff really happens at the Nailed convention. So go to NAILD.org. That's nailed.org for information on LS1, LS2, joining the association, LS controls, all that kind of thing. This has been episode 28, and we want to thank Dr. Paul Rudy from SLD Laser. Wow, that was a good business case. I got to hand it to him. I was really skeptical before we came on, but Dr. Rudy, you really laid it down why laser has got a future in this business. Episode 28, Get a Grip on Lighting.